Hello. In this video, we are going to be discussing the three chord properties that you have listed in your note sheets. So you want to be looking at page 12 in your notes packet. And first thing we're going to do is look at this diagram in which we have a circle with the center at A. We have two chords in our picture. We have chord HI and we have chord BC. And we have some different measurements recorded. The two chords, these are purple in the diagram, so their measurements are also purple. We have the length of BC and HI listed for you. So BC right now has a length of 2.2 centimeters. HI has a length of 4.3 centimeters. We also have that this segment here, AD, has a length of 2.8, and the distance from point A to chord HI is 2.1 centimeters. Now it's not showing here on the diagram, but remember distance, that is the same thing as what we're doing here with this segment AD. You are measuring from point A to the point that is perpendicular to this chord. So you don't see it in this picture on this side, but it is the same thing. So kind of visualize another segment connecting these together that are perpendicular. Okay, so we're interested in what the behavior is as the length of the chords change. How does that relate to other pieces in the circle? Okay, so now over here we've got another thing going on, and we've got this graph with point G, and point G, if you look at this graph, the x-axis is representing the length of chord BC, and our y-axis, what G is actually recording, is the distance the chord is from the center point on the circle. Okay, so let's see what happens as this length of BC, let's see what happens as this length increases. So the x values on this graph get bigger. Let's see what happens to the chord. So we see here the length of our chord is getting bigger, and what happens to point G, those values along the y's are getting smaller, which coincides with our diagram, which shows that the distance that the chord is from the center point is decreasing. And now it's going back the other way. The chord is decreasing while the distance from the center is increasing. Okay, which makes sense. You know, if you're going to shrink the length of the chord, of course it's going to move further away from the center of the circle. Okay, so now if we're looking at chord BC, let's see what happens when BC is equal to the length of HI. So here we're almost there. Oh, back up just a little bit. We've got, there we go. So here I've stopped it right at the point where BC and HI have exactly the same length, 4.3 centimeters for both segment BC and HI. Okay, so look at the diagram. What do you notice? You have two chords that are congruent. What do you see with respect to distance from the center? The measure of segment AD is 2.1. The distance from the center of the other chord is also 2.1. So equal chords have equal distances from the center point. Again, makes sense. Okay, okay, so now let's talk about what happens if we look at the intercepted arcs. So let's say we want to look at this intercepted arc HI. First I'm going to construct, choosing the points, construct an arc on the circle, and I'm going to measure that arc. I want the arc angle. So the measure of arc HI is 89 degrees. Now let's come over here. We have segment CB intersect. Okay, so here I have arc CB. I'm going to measure the arc angle, and what do you know? Equal degree measures of the arc. So when my chords are congruent, not only are their distances from the center the same, but the measure of their intercepted arcs are also the same. Okay, so that's another conclusion that we can draw. All right, let's see. Last thing we want to look at, if you're looking at your notes handout, the middle property we haven't really talked about. Looks like we have a picture of a chord and a diameter. So let's say, and it also appears to be perpendicular. So let's do this. Let's select this chord, and I want this midpoint. I want to construct a perpendicular line. Looks like that perpendicular line passes right through the center of the circle. Let's see if the same thing would work on the other side. Let's go to segment HI. First, I need the midpoint. And now I want to construct the perpendicular bisector of that. So perpendicular line. Again, it seems to pass through the center of the circle. So here you have a line, two lines that pass through the center of the circle. They both pass through 2 points on the circle. It appears that those are also, what can we call those? It's another line or a segment passes through the center of the circle. That's a diameter. Okay, so let's go to our notes and let's write down some of these things that we just found out. Okay, so special chord property number 1. We have a picture that has congruent chords listed for us. So what was the conclusion that we drew about that? We said that if we have congruent chords, then they have arcs. The intercepted arcs are going to also be congruent. So congruent chords intercept congruent arcs. Okay, and the other thing that we said about congruent chords, so we can go ahead and label that in our picture. Let's pick another color, get some pink. So that arc will be congruent to that arc. Arc HG is congruent to arc DE. So HG congruent to DE. Okay, the other thing that we said about congruent chords is that their distance from the center is going to be equal. So let's go down to our third picture. We'll go ahead and fill out this one next. Here we have a picture with chords that have equal distance from the center. Okay, that's also true. So this is an if and only if statement. So let's write down that property. If chords are equidistant from the center point, then the chords are congruent. So chords, the same distance from the center are congruent. And the opposite would also be true. So chords that are congruent are the same distance from the center. And chords congruent are the same distance from the center. Okay, so that's an if and only if in your textbook. Okay, so now let's look at the second chord property, the one here in the middle. Chord property number 2, this is the one that we wanted to talk about, the perpendicular bisector. So we said that if we have a chord that's a perpendicular bisector, or I'm sorry, we have a segment that is a perpendicular bisector of a chord, then that segment would end up being the diameter of the circle. So we can write that as perpendicular bisectors of chords are the diameter of the circle. And vice versa. So, and diameters of a circle are perpendicular bisectors of chords. Okay, so when you're labeling your diagram, not only is this diameter, um, not only is this segment HG a diameter, but it also is going to be the bisector of that chord, and we know that's going to form a right angle. Okay, and vice versa. So if they give you, so let's say that they give you that this is a right angle and that this is cut in half, then you're able to conclude that this HG will then be a diameter. Okay, that's going to be a way that you can verify that this segment HG is actually passing through the center point D, which will be important on some problems that we'll see later on. Okay, so there you have it. You've got your 3 chord properties. You're going to want to bring these filled out with you to class, and then tomorrow we are going to work on some problems together in small groups. So we'll see you then.